let's consider the electric field of a ring of charge. So I've drawn a ring of charge in orange. This ring is in a plane that is essentially hard to see here. This should be on an angle. It should be a circle. It's on an angle. And so it's in what we'll call like the X and Y plane. So I've drawn what is considered to be kind of the Y. So this will be the Y direction. And so we can call, depends on how we want to kind of notate things. We could call this the Z dimension. And then there'll be another dimension which I haven't really drawn because I think it'll make things kind of difficult, but it'll be like this, and that would be our X. So you can see that we have an X. Well, maybe I will keep it there for trying to keep things a little bit easier to see. I'll just draw it softer. So you get a sense that the ring is in the XY plane. And then we're thinking about this Z plane as going through the center of that ring. Okay, so let's take a look at what the electric field would be at this point along the Z axis. And so we could define a few things here. Let's start just by defining that the distance here from this center point to this point, we'll just call that Z. Some distance along the Z axis. And I've already drawn in R for the radius of this ring. And really that's the distance in the Y dimension from the center point to the edge of the ring. So what we can do when considering the electric field at that point is to look at the contribution from a little small space along the ring. So we could say, well, what is some sort of dq right there, and we can, that was intended to be a square. So a little component of the ring there, and we'll say that this is some sort of dq. We've got a q of charge along the entire ring, and some little piece of it will be in this little piece of the ring. And so how is that going to contribute to the electric field at that point? Well, we're going to be able to, let's just try out a line along there. Okay, so we'll draw a line going from our dq to our point. Okay, and so we're some distance away, and in fact that distance away is going to be the result of looking at square root of r squared plus z squared. Gives us this distance away from the point. Okay, and so we'll do this in blue, I guess, for the electric field. It's going to produce an electric field in that direction. At the same angle, we'll try to make that very similar. And so this will be some sort of dE because of our dq. And this dE is going to have the components along the, I guess this would be, in this case, I don't want to do that in dotted. We'll back up a second. So we're going to draw just dotted lines where we'll have some components, and then we're going to note this as some sort of dE in the Z direction and a dE in our Y direction. Okay, and this angle here is going to be the same in both. So we're going to have a theta here, and we're going to have a theta there. It's the same angle. So if we define it for one, we've got the other. All right, so our angle is going to be found by looking at cos theta. Say cos theta is equal to z over r squared plus z squared to the 1/2. Okay, so that's our angle in both cases. All right, so let's start out by considering what the electric field would be, just considering that point and a point charge. We've done that kind of work before. Well, we would have a electric field that's equal to K, Coulomb's constant, a Q divided by some sort of distance squared. That's the electric field caused by some point charge. But in this case, it's a bit different. In this case, we're going to consider what is the dE, so the little component contribution to the overall electric field caused by dQ, the little component of the total charge at that location. And instead of r squared, we're going to put this in terms of the two variables we have to work with, which are r squared and z. So now our equation for the component of the electric field is in terms of things that we know. Now, of course, we want to look at the component of the electric field in the z direction. And the reason for that is that when you start to add up all of these dQs, you'll notice this problem has a really important symmetry. That symmetry makes the problem significantly simpler because we can consider that there's a symmetric little dQ down here, and that's also going to produce a dE, and that's going to be here. And the component in the y direction is going to cancel with the component in the y direction from our original dQ. And you can go to any point along this ring and find that there's always going to be a matching dQ. Got a little dQ there, and we've got a symmetric dQ there, a dQ there, a dQ there. There's always going to be a symmetric component to the ring that's going to cancel that x or y component. And we're left only with the z component of the electric field. Okay, so that's why we're going to be interested in Ez. So if we were to then convert this equation to an equation for dEz, we need to consider the angle. So we're going to add a cos theta term. Okay, now the cos theta term can be rewritten, as we see over there, as incorporating z and r squared, which is preferable. It will make it easier for us to do the integration. That's our dE in the z. Okay, so let's combine these two terms so that we get an equation that is k dq z, and that's all over r squared plus z squared 3/2. Okay. Now at this point, we can note that the only value that's changing here, so if we want to now integrate to get our total E, so we're going to integrate And note that which variables change. dq is the only variable. Okay. K is a constant. Z never changes. That's a consequence of the geometry of this particular situation. You can move around the length of the ring, but the location along the ring doesn't matter. What matters is the distance between the ring and the point, and that never changes. Z and R remain, and the combination of them that gives you the distance between dq and that point remains the same. So those don't vary. So that's actually quite nice. So let's go back into this equation. We're going to integrate both sides. And when we do that, we get the electric field for Z. And by the way, as we discussed, due to symmetries, that's actually just equal to the electric field. And so then we have an integral of K Z dq over r squared plus z squared to the 3 halves. However, all of this is able to come out of the integral except dq, because none of this is going to change as we do the integration. So we have the integration just around the ring of dq. So that means it's just going to be q. So we have k q z over r squared plus z squared to the 3 halves. And there we go. That's the electric field along that line for a ring of charge, making use of the fact that there's useful symmetries that simplify this problem. Now, let's do one last thing. Carve a little bit of space off here. And let's take a look at, consider if r, so this radius of this ring, goes to 0. Okay, well, let's just bring this equation over for a moment. All right, so if r goes to 0, what's going to happen? Well, it's going to get smaller and smaller and smaller, and so this is going to be 0. And then we have z squared to the 3 halves. And so then, due to some nice cancellation, we have e. I'll draw this a little bolder to be consistent. Got a bit of room here. So we'll have the electric field of this very, very, very small ring is going to be k q z over z cubed. Interesting. This z cancels out with one of these, and we get z squared. Now that looks familiar, doesn't it? That looks like a point charge. Okay, so that's the electric field of a ring of charge. There's one last thing to do, and I'd like you to try it, and that's to determine where the maximum electric field is along Z. Because if we look at this situation, there's some interesting features. First of all, let's take a look at the center. if you are exactly in the center, what's the electric field? 0. Because the components of all the little DQs are going to have a symmetric partner on the other side of the ring that's going to identically cancel out that contribution. So you add them all up and you get 0. And so at the center, it's a 0 electric field, and then as you move away, the electric field magnitude increases. But we also know that if you're really far away, very far away, eventually it's basically 0, because the magnitude of an electric field falls away with distance. So that means somewhere between z is equal to 0 and z is equal to a big number, there is a maximum. How would we find a maximum value using an equation that describes that value? Well, that'll be an exercise